All right, so today we're going to look at just a single section, okay, just 1.5, which is on quadratics and how we can transform them. So what we're going to look at in this section is basically how you can shift a graph left, right, up, down, how you can stretch it or compress it. And we're going to do it with just quadratics today, okay, just parabolas. But what I'm going to show you today applies to any function. You can shift a square root function, left, right, up, down. You can shift a sine wave, left, right, up, down. Okay, you can do all the same stuff I'm going to show you today with a ton of other functions. And we're going to look at all those functions throughout the year. Okay, so this is really important for transformations for the whole year. Okay, but a quadratic or a parabola is one you're probably familiar with, so it's a good place to start. Okay, so that's what a quadratic function looks like. It's of the form ax squared plus bx plus c. Now, b and c can be any real number that you want. And a can be any real number except 0. Why can't a be 0? What would happen if the coefficient of x squared was 0? Yep.
It wouldn't be a quadratic function.
Yeah, it wouldn't be a quadratic. If you made a 0, you would wipe that out, and now you turned it from a quadratic into a, what would that be? Yeah.
A linear function.
Yeah, it would be a linear function, assuming b wasn't 0. Right? So a, b, and c can be any number that you want, except a can't be 0. That's what that says right there. A, b, and c are elements of the real numbers, and a can't equal 0. All right, so let's graph y squared. Y equals x squared, sorry. All right, so if you have anything else in there, you can just clear it out. All right, so y equals x squared. And the graph of that looks like that. Now, what I'm going to do with that is I'm going to change it from an x to a negative x. And I want you to see if you can tell the difference. In order to do that, I need to put parentheses just like that. And now inside there, I'm going to put a negative x. What did putting a negative do to the picture? Anybody see a difference? Jan? No, there is no difference, and that means something here. Does anybody know what that means if you can plug in a negative x for x and the picture looks exactly the same?
A negative number squared and its positive number squared would be the same thing.
Okay, so if you square a negative number or you square a positive number, you get the same result. And geometrically, what does that mean about this picture? If this picture is the same as the other picture, it has to do with this y-axis. This y-axis is something special in this picture. It's a something. Yeah?
Axis of symmetry.
It's an axis of symmetry. All right? So anytime that you can change x to negative x and the picture looks exactly the same, that means your y-axis is a line of symmetry. Now, if I did something like, I'm just going to do zoom 6. And if I put the negative on the outside of parentheses, okay, that would do something a little different. I can leave the negative on the inside. It doesn't make a difference. That flips the graph. Okay? Anytime you put a negative in, it does flip the graph. But if you're flipping it over something that's a line of symmetry, you can't tell the difference. In this case, the x-axis was not a line of symmetry. So when you flip it, you can see that it looks different. Okay? You can't tell that it looks different when you do it over the y-axis. If you wanted to see it looking different, I would have to graph something that's not symmetric. Okay, if I graph that and that, negative x cubed and x cubed, you will see a difference between the two because the y-axis is not a line of symmetry. That's one. And that's the other one. So they're mirror images of each other over the y-axis, but you can see the difference because it was not a line of symmetry. Okay? So any questions on that? All right. So in a parabola, the low point, okay, that's called a vertex. The vertex can also be the high point if you take the parabola and flip it, okay, the way I've shown here. And hopefully from what I just did on the calculator, you know how to flip it now. Putting a negative in front will cause it to flip over the x-axis. Putting a negative on the inside causes it to flip over the y-axis. Okay, so any questions on the idea of a vertex? All right. So what we're going to kind of play with now is changing the coefficient of x squared. Okay, we'll just try changing it and see what happens. Does anybody already have an idea of what's going to happen when you change the number in front of x squared? How about Caleb? You have a guess what might change? So how will that look different? What will the look be?
A wider curve.
Okay, so maybe a wider curve or a narrower curve. Let's try it and see. So I'm going to graph x squared. Then I'm going to graph 1/3 x squared. Let's just start with that. Okay, so the graph in blue, that's my original. And by putting a 1/3 in front, what did it do? How would you describe? Yeah?
The curve expanded out.
In which direction?
What?
Like it stretched out which way?
Both the right and left.
Yeah, horizontally. Okay, so it stretched out horizontally. Or you can think of it as it compressed it vertically. Imagine that blue parabola was flexible and you pushed down on the top of it and compressed it, it would squeeze out sideways like that. So now what do you think is going to happen if I put in a 2x squared? Yeah. Horizontally, what would it do vertically? It's going to stretch. So this one is going to look taller and skinnier. It's going to be inside the blue parabola. Okay. So the effect, we're going to describe it as having a vertical effect. And if you put in a number in front that's bigger than 1, it will stretch it vertically. If you put in a number that's between 0 and 1, it will shrink vertically. You could say the graph is shrunk down. Now, I already kind of showed you what happens if you do a negative. We're not going to talk about complicating it with a negative yet. Okay, so any questions on what putting a number in front of x squared does? Either a number bigger than 1 or between 0 and 1. Okay. try this. Actually, I already kind of did it with you, but what was the effect, maybe we don't need to do it again, of putting a negative in front like that? Yep. Caused it to flip. And which axis does it flip over if you put a negative in front? Yeah? Yes, it will flip over the x-axis, or you could say reflect. So I think I graphed one of these, like negative x squared, and it opened downward. Okay, so putting a negative in front causes the graph to open downward. We're not going to talk too much about reflecting over the y-axis in this graph, because if you don't shift the parabola and you leave the vertex at the origin, reflecting it over the y-axis does nothing. It looks exactly the same. So parabolas are not the best graph to talk about reflecting over the y-axis if you're not going to shift them. Okay. All right. So kind of problem you might see on a test is using what we call the parent function, okay, the basic parabola without anything done to it. Explain how you would get the graph of negative 5x squared. Okay. How many things are happening to turn the graph I underlined in red into the one I underlined in black? I have a guess how many things are happening there. How about Abby? What do you think? How many transformations does it take to change the one in red into the one in black?
Well, you do a reflection.
Okay, that's going to be one thing.
It will be.
Well, there's going to be some kind of stretch. I won't say yet if it's going to stretch or shrink. So how many transformations is it? Two. So there's two transformations to turn those the graph of y equals x squared into negative 5x squared. Okay. And we're going to start with the 5. Okay. I'm going to tell you the order you need to write a transformation in because it does matter. It's kind of like PEMDAS. The order you do it in can make a difference. So let's start with the 5. Julianette, what would the 5 do? So remember we said if the 5 is like our A value. It's the number in front. So we had two cases, if it was bigger than 1 or between 0 and 1. You want to help her out? What's the 5 do? Yeah.
It's going to shrink horizontally.
Okay. And then how else did we describe it? Besides that way. The way that I had on the board. Not sure? Sam?
Stretch it vertically.
Yeah. So it's going to, I think I had it here. Where was it? Right here. So if A is greater than 1, the graph is stretched vertically. If A is between 0 and 1, it's compressed. Okay, it's going to shrink. So it's going to stretch vertically. And we say it stretches vertically by a factor of 5. So vertical stretch. But you have to tell me by how much. Okay, by a factor of 5. And now the second thing that's going to happen is that negative. Dylan, what's that negative going to do?
It's going to reflect over the x-axis.
Perfect. Reflect over x-axis. So those are the two transformations you would have to do to turn y equals x squared into y equals negative 5x squared. Okay, any questions on that one? Yeah.
So
So if that was a problem in a test, that's exactly what we had right there.
That's exactly what I'd want you to write. Yep. If you only said, for example, reflect, I'd only give you half credit for that part of it, because reflect doesn't tell me over the x or over the y-axis. Same with vertical stretch. You have to tell me by how much. Okay. And don't just say stretch by a factor of 5, because there's also horizontal stretches, which we're not really going to get into with parabolas. Okay. This is a vertical stretch. All right, let's look at the calculator and kind of play around with these two graphs and see what's happening here. So we've got x squared. Anyone have a guess what x squared plus 2 is going to do? Yep. Okay, let's try it. So we'll go to y equals. Keep x squared because that's the good one to compare to. And let's put in x squared plus 2. Okay, so the graph in blue, that's going to be the original. And the graph in red, we can see that it has been shifted up 2. Okay? So we'll write that down, and then we'll kind of write down a rule to generalize this. So to get y equals x squared plus 2 from y equals x squared, we want to shift y equals x squared up 2 units. All right, and the other one, okay, to get y equals x squared minus 3 from y equals x squared. You're always going to be comparing it to the y equals x squared. Anyone have a guess what we would have to do to get x squared minus 3? Yeah, Caleb?
Shift it down 3.
Shift down 3. Shift y equals x squared down 3. Okay, these are what we call rigid transformations. They don't distort the graph. They don't stretch it. All they do is take exactly what you have and move it somewhere else. Okay, in this case, shifting up or shifting down. Actually, I have it over here. So vertical shifts, I just said these are rigid motion transformations. And the idea is that if you have x squared plus k, if k is a positive number, it's going to shift up. If k was a negative number, it's really like you're subtracting k, and it would shift down. Now, why did I put absolute values around when I shift down? Any guess why I put that there? Yeah?
Because you can't look at negative units.
Yeah, you don't want to say something like shift down negative 2 units. I'm not even sure what that really means. All right? You can shift it up 2 units, you can shift it down 2 units, but you can't shift it negative 2 units. Right? So always describe the shift using a positive number for k, and then if it's moving in the negative direction, you put the word down, and that takes care of the negative. Okay? So any questions on the idea of vertical shifts? And these are going to work exactly the same for every function we study all year. Compared to the basic parabola, that one is shifted up 2. Compared to the basic square root function, that one is shifted up 2. Okay? Doesn't matter what function you're working with. Okay? Compared to the sine function, that's the sine function shifted up 2. Okay? Same idea will apply to all these functions. Okay. What do you think's going on here? where we have a plus and a minus, but now it's inside the parentheses. Any guess maybe in general what's happening? Maybe not specifically which one is which, but just a general idea of what's happening?
Maybe it shifts left and right.
We are shifting left and right. Okay? Minus 3. Which way do you think minus 3 is going to go? Sam? Left? Which other way could it go? Yeah? Right? Well, it's one of those two. So let's graph it and see what happens. So, whoops, I didn't want to get rid of that. So we got x squared. Now let's do x squared minus 3. So x minus 3 squared. Okay, so there's the original. There's the new one. Which way did it shift? It shifts to the right. And that's going to be kind of something we have to deal with when we do horizontal shifts all year. It does the opposite of what you would expect. Okay? So the way I look at it is I look at the number after the minus sign. And I say that's a 3. Okay? Just looking at the number after the minus sign, it's going to shift 3 units to the right. All right? So we just got to kind of get used to that. So y equals x minus 3 squared. Shifted 3 units. Bless you. 3 units to the right of y equals x squared. Okay, and how about y equals x plus 2 squared? That's going to be shifted which way? Yeah. It's going to be shifted left. So again, if you think of this as like the number after the minus sign, and the way I would think of it is like this. Think of it as x minus minus 2. That's a plus 2. So always think of writing it, one way to always think of it is put the minus sign in, look at the number after the minus sign. It's a negative. Negative is going to shift left. Look at the number after the minus sign and the one above it. It's a 3. 3 is positive. It's going to shift right. Okay, so that's how I think of it. Look at the number after the minus sign. So y equals x plus 2 squared is shifted 2 units to the left. Forgot the word up. So 2 units to the left of y equals x squared. So again, horizontal shift, that's rigid motion. It's not distorting the graph. And the idea is that if you look at the number after the minus sign, block the minus sign. If it's a positive number, it's going to shift right 8 units. Okay. If you look and you had something like this, again, block the minus sign right after the x. You have a negative number, in this case negative 5, that would shift left. Okay, so just want to focus on what I just circled. And just like with shifting up and down, don't say shifting left negative units or shifting right negative units. Left and right takes care of whether it's positive or negative. Okay, so we've looked at how to shift it up and down, how to shift it left and right, and how to stretch it up and down. The only thing we haven't looked at is stretching left and right, and that's not something we look at really with parabolas. Okay, so that's most of what we're going to need to know. The other thing is that when you shift the parabola left, right, up, or down, the vertex also moves, right? Because that's part of the parabola. The way you can figure out where the vertex is going to be is just focusing on how much did you shift left and right? How much did you shift up and down? So your vertex starts at 0, 0, and all you do is, let's say you shifted it right 2 and up 3. Well, think in your head, if you start at 0, 0, where does that go if you shift right 2 and up 3? It would go to the point 2, 3. Okay, so HK is the coordinates of your new vertex. And what kind of line of symmetry does a parabola have? Vertical or horizontal? Yeah, vertical. And which transformation would affect where the line of symmetry moves? Would shifting left and right affect the line of symmetry, or shifting up and down? Yeah, left and right. Shifting something up and down, if that's a line of symmetry, and you shift up, it's still the same line of symmetry. Same thing with shifting down. So the only thing that affects the line of symmetry is when you shift left or right, and that's controlled by H. K has nothing to do with the line of symmetry. And we mentioned this yesterday, because it's a vertical line, the equation is x equals H. Any questions on that? So, I want to find the vertex and line of symmetry for this graph. Can somebody tell me, first of all, which way has this graph been shifted? How many units left or right, and then how many units up or down? Rebecca?
2 minutes left.
Yep, 2 units left and 3 units down. So if your coordinate started at 0, 0 for the vertex, and it did what you just said, where would that coordinate end up? Yeah. -2, let's see, -3. So there's the coordinates of your vertex. Line of symmetry, Trevor, always starts out with what letter equals? No, because that would be a horizontal line of symmetry. X. So X equals. And how about, Anna, what would be my line of symmetry here? X equals what number? Do you remember what letter I put down affects the line of symmetry? It was X equals. Okay, so line of symmetry, X equals H. Okay, so it's the H value. So if we go back, my H value here is.
What is the H value? I'm sorry, I'm like kind of lost.
The H value
Yeah.
is
Oh, that number, okay.
the first number after you find the vertex, or it's the number after the minus sign.
So
It's -2. Okay, so my line of symmetry was at X equals 0. My line of symmetry was the y-axis, but since the graph was pushed 2 units to the left, my line of symmetry is also now 2 units to the left. Okay, everything moves with that graph. All right, let's try this one. How many transformations would it take to turn that into that? Well, Sam? 2, yep, it's going to take 2 transformations. And I'm going to give you a hint at what the order should be. but in a little bit, I'm going to tell you the exact order to always do the transformations in. So let's start with inside the parentheses, if there are any. In this case, there's not. So now I'm going to go to the number in front of the x squared. What is that 5 going to do? How about Dylan? What's the 5 going to do?
It's going to stretch it vertically by a factor of 5.
Perfect. Vertical stretch by a factor of 5. And then what about the plus 4? How about Tanya? What's the plus 4 going to do?
It's kind of make it go up more.
Yep. Shift up 4. So as long as you tell me that it's a shift, direction, and how much. So it's shift, we're going up 4 units. Any question on that one? And the order does make a difference. Right? Just think of like PEMDAS. If you do a calculation, it makes a difference. All right. How many transformations are happening here? How about Tessa? Do you have a guess how many transformations we're doing? 3? It depends if you do 2 things in one step. But I think here, if we break it down, we're looking at 4. Okay, if we really break everything down. So starting inside the parentheses, what is that minus 1 going to do? Yeah, we're going to shift right 1 unit. Yep. Shift right 1 unit. Now we go outside the parentheses and we deal with what's immediately next to the parentheses, which is a 3. The negative is something else. What's the 3 going to do? How about Caleb? What's the 3 going to do?
The 3 is going to shrink it vertically by a factor.
I like the idea it's going to do something vertically, but it's going to stretch. So it's going to make it tall and skinny kind of thing. So it is going to do vertical, but it's going to be vertical stretch by a factor of 3. Okay, how about the negative in front of the 3? We saw one earlier, a couple with negatives. Jane? That's going to reflect over the x. And then the last thing is the plus 4, which is a shift up 4. So this problem pretty much illustrates all the different transformations you could have except for a reflection over the y-axis, which could have happened if I did something like that, putting a negative on the inside parentheses. Okay. But in general, these are the steps to follow. Always do your horizontal shifts first. Then you do your vertical stretching, shrinking, which is what we did in step 2. Reflecting over the x-axis, if necessary. These are all if necessary. If you don't have it, you don't have to worry about it. And the last thing is always a vertical shift. If you're wondering where a reflection over the y-axis would come in, that would be right here. Okay, we didn't do some of the horizontal stuff. We could have done a horizontal reflection, could have put that in there. And we also could have dealt with a horizontal stretch, okay, but we didn't put that in there either. Okay, so in order to do this, we're assuming that our example is written in what we call standard form. Okay? It's written like that, where you can clearly see the A, the H, and the K. But what if you had something like 3x squared plus 12x minus 18? That's generally how you see it when you're going to factor it. But in order to figure out all the transformations on this one, we have to complete the square. We have to make this look more like that. We have to have the set of parentheses in there, squared, and all that stuff. Okay, so I'm not going to write down all the steps on how to complete the square. I'm going to go through an example, but I'll show you from that. Okay, does everybody have what's on the left? All right. So the important thing to remember is that when you complete the square, make sure you keep the equation balanced. Okay, anything you do on the left, you're going to make sure you do on the right. Okay, does anybody remember completing the square? Usually you use it to solve a quadratic equation. We're just using it to rewrite something in a quadratic. We're not actually solving it. All right, so let's take a look at our example, which is that. Okay, first step to completing the square is the number in front of x squared has to be a 1. Is it a 1 in this problem? No, what is it, Sam?
3.
A 3. So I'm going to factor it out. Okay? So I'm going to, let's see, how do I want to do this? Actually, you know what? One thing before we even do that, I'm going to factor the 3 out, but I'm also going to put the constant on the other side. Okay, that's the first thing I'm going to do. Put the constant on the other side by adding it. And I could factor out a 3 at the same time of what's on the right, but I'll do that as a separate step. So step 1 when you're completing the square, put the constant on the other side. Basically, I just added 18. Pretend like you're solving a quadratic. Pretend y is 0, and you just added 18 to the other side. That's all. Okay, now we're going to factor out the 3. And you know what? I can do it. I'll rewrite it again. Now we have to find the number to complete the square. Leave a little bit of space because you're going to add something to 18. And leave a little space inside the parentheses. So to complete the square, it has something to do with this number. Does anybody remember what you do to that number? And it's two things. So the first step is to take half of it, which gives me how much? 2. And then does anyone remember what you do with that? Yeah? You square it. Okay? So in this case, not much interesting happened, but you take half of 4, you get 2, and then you square it, and you get 4. Now, what did I just add on the right? Yeah? Not quite. I put a plus 4, but that's not what I really added on the right. Dan?
12.
Why did I add 12?
Because the first one side of the parentheses.
Right. anything that's on the outside of the parentheses here is applied to what's on the inside. So by putting a +4 on the inside, I really added 12 on the right. So to balance it, I put 12 on the left. So now I get 30 equals 3 x squared plus 4x plus 4. And x squared plus 4x plus 4 should now factor very nicely. It should factor into x plus something, and they're going to be the same. Does anybody see what x squared plus 4x plus 4 factors as? Yeah? Times. X plus 2 times. Yeah. Which one is it? Is it x plus 2, or x plus 2, x minus 2? Yeah? Plus and plus. X plus 2, x plus 2. So we could just say x plus 2 squared. And now the last step is to put the 30 back on the other side. So what I have now and what I started with should be exactly the same thing, except now I can see the vertical transformations and the shifts up, down, left, and right a lot easier. Okay, so let's start with the plus 2. Okay, Jahan, what's the plus 2 going to do? It's going to shift it left 2 units, yes. Shauna, the 3 in front.
Stretch it
By how much? Yep. So stretch, vertical stretch by factor of 3. And the last thing is to shift down 30 units. You can't really tell that by looking at the original, 3x squared plus 12x minus 18. You really need to rewrite it to see that. And if you want to double check what we did, graph what's in the box, graph the original problem, and they should look exactly the same. So that's how you complete the square. If anybody needs more help with that, let me know. But again, you got to know how to complete the square for these problems. And you don't always have to factor out a 3. This is like the worst case problem. If you had to complete the square with a problem like this, you can skip the first step of, well, you can skip the second step, which is factoring out a 3. Your first step right here is just move 18 to the other side and then go from there. You don't have to factor out a 3 in that case. These are 2 formulas you can use. It's kind of a shortcut. If all you want to find is the vertex and the line of symmetry. Okay, I don't really use these formulas too much. But if you had it written in the form of the problem we just did, ax squared plus bx plus c. You can use these formulas to find the vertex and line of symmetry. Again, they're not really formulas that I spend a lot of time memorizing or would even really bother with too much. But they're there in case you did want to use them. And the last thing, while we're talking about quadratics, is quadratics, when you draw them, can cross the x-axis up to how many times? The graph of a parabola. Yep. It could cross twice. What's another situation? How many times could it cross? Yeah? Not at all. And it could also cross once. By cross, we mean it just touches it and goes back up. So where it crosses the x-axis, we call that a root or a zero of a function. Okay? There's some x value right here that you could plug in, and when you do, you would get 0 for y. Okay? So it's a value for x such that when you plug it in, you get 0 for y. And quadratics can have 0, 1, or 2 roots or zeros. And the quick way to tell how many times a graph is going to cross the x-axis, it doesn't tell you where it crosses it, but it does quickly tell you how many times it would cross, is to do this calculation out. B squared minus 4ac. Does anybody recognize that, b squared minus 4ac? Yeah, where is it from? Yeah, it's from the quadratic formula, and specifically, it's the thing that's under the root. So if the b squared minus 4ac comes out less than 0, think about what would happen in the quadratic formula. You'd be taking the square root of a negative. Can't do that. If b squared minus 4ac came out to exactly 0, you'd be taking the square root of 0, which has one answer. If b squared minus 4ac came out positive, like let's say an easy number, 9, when you take the square root of it, there's two answers, positive 3, negative 3. So this formula will quickly tell you how many times a graph crosses the x-axis. And the last one was just an example. There's one like it in the homework, so what we can do is you could just do the one in the homework, and if you get stuck on it, we'll go over it in class tomorrow. Okay, so don't worry too much if you get stuck on the word problem tonight. Okay, so tonight it's on page 56. And it's, again, just kind of jumps around because there's a lot of problems, but I didn't want to give you a big stretch of them, so it just jumps around. So 1, 2, 7, 8, 10, 11, 16, 18, 21, 22, 28, and 33, 40, 41, 44, and 60. Okay, so the video will be online probably in about 10, 15 minutes if you need to double check anything.